Okay, so in this lecture, I want to touch on or kind of introduce us to the chemistry at carbon that happens with enolates. So let's first talk about practical applications, like what are some common bases we can use to generate enolates? Okay, so again, the goal is to take a typical carbonyl compound and look at the alpha position, which has the acidic, I'll put an aldehyde, sure, acidic alpha hydrogen, just to contrast that with the aldehyde hydrogen I've drawn on the left. Okay, so what we're going to do is treat this with some sort of base to generate an enolate. And when we do that, we get this structure, which can be shown as two resonance structures. The one on the left is a little bit more helpful for the class. The one on the right is a better resonance depiction. Sorry for the zoom in there. Okay. So what bases do we use? The answer is there's tons of bases we can use, but we're going to just stick with two for the most part in this class. So the common bases we need to know are good, old, reliable, sometimes reliable sodium hydroxide. Sometimes it generates, but it generates water after reacting, and that's not good. Oftentimes it's that water that's problematic. So it generates water after reacting, and it's usually not basic enough. Now, it turns out for the aldol condensation lab we try to do in class, we can actually use sodium hydroxide and get away with it. So it's usually not basic enough, though. So instead, what we have to do is go to another base, which is fairly common and highly reliable, and that's LDA. So LDA is lithium diisopropyl amide. So the amide implies we have an N with a negative charge in this case, not the usual amide functional group. It's a little bit annoying. Lithiums are counterion, and we have these two isopropyl groups that help with some effects. Okay, so here's what the structure looks like. We have an isopropyl group on a nitrogen here, isopropyl group, and then we have a lithium. So this is LDA. Now, what I like to do is think about it as a nitrogen with a negative charge, and then the lithium is countering that. It turns out that in reality, we have a lot of covalent character between that nitrogen-lithium bond. So this isn't the most accurate depiction, but it's super helpful for understanding the reactivity because it tells us that we have a really basic nitrogen atom. And so that's going to be our basic atom that interacts with the acidic, in this case, alpha hydrogens. Now, LDA is easy to make. It's inexpensive. I suppose it's kind of an organolithium, but it's more like a lithium amide. So in that sense, it's safe. It's much safer than other lithium bases. So this won't react with moisture to sort of detonate. And it's a strong base, so we don't have to worry about base strength. But here's why I really like it. It's very easy to control the stoichiometry. Okay, so what that means is that we can control this reaction much more easily. So we can take our carbonyl of interest, like for example, acetone, and we can add LDA to it. Now I'm going to add, for every 1 mole of my carbonyl, I'm going to add 1 mole of LDA. And what we say is we have an equivalent loading then, or we say we have 1.0 equivalence, which is in equiv with a dot at the end of it. So I don't think you need the dot because nothing really, equiv isn't a word. Whereas like cat's a word. So if you want to abbreviate catalyst, you have to put a dot at the end of it. Okay. So technically you don't have to put a dot at the end of equiv. Whatever, who cares? Okay, so 1.0 equivalence. That just means for every mole of starting carbonyl, we're going to add 1 mole of lithium diisopropyl amide, or LDA. And that's going to generate our enolate intermediate, which will be adducted to lithium, which can then easily add to an electrophile. And unless we're using something special like a silicon electrophile, we're going to see that electrophile then add to the alpha position. Okay. So this overall reaction, which is electrophile substitution at the alpha carbon, this overall process has 2 steps. In step 1, we add LDA to generate the enolate. Okay. And then in step 2, we add our electrophile to react with the alpha carbon. Okay, now what's cool about using LDA is that LDA and its conjugate acid don't typically react as nucleophiles. LDA and its conjugate acid are poor nucleophiles. So the reason why we use those isopropyl groups on LDA, and the reason why I highlight LDA in particular, is it's got so much steric hindrance that it's not going to serve as a nucleophile and do some other stuff to annoy us when we're trying to study enolate chemistry. Okay, so it just kind of does its thing. The enolates do their thing, and everybody kind of moves on with their life. Okay, so a typical reaction would be an SN2 reaction of enolates with haloalkanes. So this is a callback to one of the most important reactions in organic 1, which is the SN2 reaction, where you take a nucleophile and you add it to a haloalkane. We did the same thing with the Williamson ether synthesis at the beginning of the semester. So this is actually a reaction we've seen several times, where we take some nucleophile and we add it to some carbon atom that's got a leaving group like, let's even draw it out. We'll put a bromine here. We'll put 2 hydrogens on the carbon. The nucleophile adds to the carbon and pushes off the bromine, and now the nucleophile is attached to the carbon with the 2 hydrogens and the R group, and the bromine leaves. So there's our SN2 reaction. Now the reason why I'm bringing this up now is we're going to let the nucleophile be our enolate. Okay. So what this is going to look like is we could take a reaction. Let's take this. And I'm going to do 2 steps. In the first step, I'm going to add LDA. In the second step, I'm going to add some haloalkane. Let's make it like this, okay? I'm going to highlight some atoms. Let's pick different colors. Okay, so what atoms did I highlight? Well, the first one I highlighted was the alpha carbon, which has my alpha hydrogen atoms, which means we're going to generate, just so I can track everything, I'm going to write the structure of my intermediate in brackets. Okay, so I have an enolate. Now you notice I don't have a symmetric carbonyl. I have something on both sides, but the left side doesn't have any alpha hydrogen, so I just don't worry about it. Okay, so I've got my enolate structure. And this is from step 1. What I want to do is let that enolate structure engage with the electrophile. And so that's going to take this carbon, which was the alpha carbon, and connect it to this carbon. And we could push arrows to do that. Because we have carbon atoms, we lose like our typical label placeholders, and bound line structures can get confusing. My point is it's easy to lose carbon atoms here because we don't have our placeholders as we're drawing structures. Okay, so I'm going to redraw the enolate now because everything just kind of stayed put. And then now I'm going to highlight, this is my alpha carbon. Using a new bond, that's going to connect to the carbon in red. Whoops, let's go back to black. Okay. The carbon in red, which was a CH2 attached to a benzene ring. I added a carbon. Sorry. You can see how easy it is to screw that up. Okay. The blue bond shows the connection between the green and the red atom. I should have just stopped and added the colors right there. But okay, so this is the final product. We form a new carbon-carbon bond, which is very powerful. Using popular electrophiles, we'll say. So this is pretty powerful technology, a pretty powerful method for making complicated molecules because carbonyls are so abundant and haloalkanes are so abundant. And here we can couple these two together using enolate chemistry by just adding one common reagent, LDA, generate our enolate, add in our electrophile, we make a carbon-carbon bond by a typical kind of run-of-the-mill SN2 reaction. If you wanted to use the alternative resonance structure, you can. Any resonance structure can give you any product. You just need a few more curly arrows. Okay, so if we had considered the alternative resonance structure, which is technically a better resonance structure, red, green. The arrows would we would just have an extra arrow to come down and make the carbonyl and then take the pi bond at the carbon-carbon, at the end of the carbon-carbon double bond, add to the red atom and push off the bromine. That would give rise to our product again. So we can go from any resonance structure to get there. Both of the resonance structures, the enolates, can prove useful. I mean, one's a better contributor, one's a better depiction of where we're going to see reactivity occur with most electrophiles, particularly when there's carbon. Okay, so that'll do it for this lecture. In the next lectures, we'll pick this up with some more advanced chemistry, namely the aldol reaction and aldol condensation reaction, which involve enolates. Okay, so until then, see you next time.